We know sorting is will arrange the elements in ascending or descending order. There will be n elements, you have to arrange in what order? First we'll go for a ascending order. In exhaustive search, it is not straightforward. We'll have more possibilities. See, for selection sort, for one input, only one output. A salesman had to travel from one city to another such that he had to cover all the cities and the cost should be minimum. Hello everyone, myself Evelyn Jacob, working as a faculty in BCA department, Vidhyaashram First Grade College, Temple of Excellence, Mysuru. Today's session is the design and analysis of algorithm, that is unit 3. So in this unit, we're going to cover all these topics. The very first topic is introduction to brute force. Next is the sorting, the selection sort and the bubble sort. Next, we can have this exhaustive search. That is what about TSP, traveling salesman problem, knapsack problem, and these are two, DFS and BFS. So, what is brute force? In the third unit, the topic is brute force. So, when I say brute force, it is a straightforward approach. It is a simple approach. And the definition of the concepts involved. So, direct problem, you no need to select the solution of it. If I say matrix multiplication, it is straightforward. That is what is called brute force. So, what are the examples? So, first it is based on the definition, directly on the definition. So, for example, I can compute the n factorial. So, if I say 3 factorial, you all know what is the answer? 3 into 2 into 1, that is 6. Then multiplying two matrices, or you can go for a linear search, searching a key. So, the very first sorting in the brute force is selection sort. What is selection sort? We know sorting is will arrange the elements in ascending or descending order. There will be n elements, you have to arrange in what order? First we'll go for a ascending order. So first we'll scan the array to find the smallest element and swap with the first element. First we'll give the input and then we'll see which is the smallest element, we'll swap, meaning to say in the first element we'll have the smallest value. So this will take from a of 0 to a of I minus 1. If I take the example of 7, 3, 2, 5, how shall I sort it? We all know that it begins with the smallest element. First is 2, next is 3, next 5, 7. So this is selection sort. So selection sort works for a smaller problems. So first we'll take a smallest element and put in a first position, that is a of 0. So a of last element, that is this is 1, 2 and 3. So a of 3 will have the largest element. So we know the concept of selection sort. If I say sorting, it's simple. But how this algorithm works? So algorithm for selection sort, what is the input? It starts with a of 0. That is first element to the last element. So what is the selection sort does? What is the output? It sort in the ascending order. So what is the input for it? It is an array. Okay, if I start with a loop, why should I start with a loop? Because more than one element. If there is only one element, no need of sorting. This is only already sorted. We no need to compare with the other element. So, this is the loop. We are starting from 0 to n minus 2. First, we'll assign minimum is equal to I. We don't write equal, we'll write this left arrow. We'll take one more loop for that to swap the elements. Swap means interchange. For j is equal to I plus 1 to n minus 1. What we have to do, each time we have to check the condition. If a of j is less than a of min, what we do is, we'll assign j to minimum. And what we have to do, we have to interchange, swap. This both are swapped. This is selection sort. First, what we do, we find the minimum element and consider that is the minimum and based upon that, if it is less, we'll swap. So that first element will always be the smallest element. Then what is the time efficiency? Time efficiency is the time taken for this algorithm. We denote by big O. Then what is N? N is the size of the array. So what is the space required here then? What is the space then? It is memory space. It is not N here, it is 1. Why 1? We have taken an additional variable, say min. It can be anything. So 1 space is given to that temporary variable. So after this sorting, we have gone for an exhaustive search. What is exhaustive search? It is also a brute force. But in exhaustive search, it is not straightforward. We'll have more possibilities. See, for selection sort, for one input, only one output. But here, in that possible solution, I have to find which is the minimum or which is the optimal. So we'll come with this exhaustive search. See, exhaustive search solution, that is search until its possible solution is exhausted. Until it is exhausted, we should keep on seeing the solution. Which is better? That will be the answer. So it is slow then. Why slow? We keep on comparing the solutions. So a brute force solution to a problem involving search for an element with the special properties. Here we have to go with the combinatorial objects, means a subset. What is subset? We'll write inside a flower bracket. It can be 1, 2 or 2, 3 or anything. This is the subset. This will have in a exhaustive search. Next. So, in the exhaustive search algorithm, we told a possible solution will be there. In that, we have to find which is optimal. So, how to find that optimal? These are the following algorithms tells you how to find it. The very first problem is TSP, traveling salesman problem. A salesman had to travel from one city to another such that he had to cover all the cities and the cost should be minimum. So that is the solution. I'll have all the solution, pick the one which is minimum. Then knapsack problem. Assignment problem is there. And in graph problem, you have 2. I'll consider with a tree and give that example. Before going to TSP, we'll understand what are the examples of it. So, in TSP, if I say traveling salesman problem, where shall I use? What is the application? It can be used in network nodes, then cities and roads. So, salesmen have to travel in cities, so we'll consider this example, cities and roads. With the people and friends, we'll have a network. Then, if I take a graph, any graph, say this is A, this is B, and this is C. It will have a set of vertices. What is the vertex? A, B, C. What is the edges? The line joining this. You can see, right? The line joining, that is the edges. It is set of edges. So, edges may have weights and direction. So, weights I'll indicate with the number, say 5. This can be 6. This is the weight of it. And the direction. Here I can also indicate a direction with the arrow mark. If it is no arrow mark, then it is undirected. So, an undirected graph, the edges have no directions. The previously what I wrote, see if I take B, D, E, this is undirected, no arrow marks. You can go from B to D and D to B. But if I write arrow mark, that is direction, it will be restricted to one path. So, coming to traveling salesman problem. See, what happens is, you will have n cities. In that n cities, I'll take A as one city, B as another city, C as third city, D as fourth city. So, what you have to do is, you have to travel from A, visit all the city, B, C, D, and come back to his original city, say A. So, how to solve this? So we have already discussed it is n cities with known distance between each pair. This is the distance. From A to B, what is the distance? It is 2. So how to find the shortest graph? Now it is exhaustive search. We have to find the which is optimal, which is the lowest. That is the minimum will be your answer. So I'll consider a tour. Tour means travel. From A to B, then B to C, C to D, D to A. So what was the cost for A to B? It is 2. Then add. What was B to C? 3. Similarly, C to D, 7. D to A, 5. When you add, it will be 17. Similarly for this path, what is the answer? 21. So how many is there? If I count, it is 17, 21, so much is there. So how much was the cities? 4 cities. So for 4 cities, how to find how much possible solution should I write? It is nothing but 4 minus 1, it is 3. What is 3 factorial? 3 into 2 into 1, that is 6. Have you got the 6 possible solution? See, if I count, it is 6. So you have to write 6 possible solution. In that, which is minimum? Here you have 17. Here also you have 17. So 17 is twice. So this 2 also is the answer. 2 also is optimal, right? So we'll discuss about the knapsack problem. So knapsack and TSP both are exhaustive search. But what is the difference between that? So knapsack is a bag. Okay, it is a bag. So what is the problem is, it will be given weight and values. What are the weights? Say W1, W2 up to Wn. What are the values? You can say values or profit. What is the profit? V1, V2, Vn. So what is the method here? What we have to follow? First, to follow, a knapsack will be given a capacity of W. See, I can't insert many items inside the bag. A bag has restriction. I should have only so much of weight. So that will be given. Capacity will be given in your input. Then, so what is the problem here? See, we have to find the subset of the items. Only one item cannot be filled, subset. So more than one item, such that you should have in your mind, it should not exceed the capacity. For example, if it is 16, the bag should not contain more than 16 weight. Weight can be kg, grams or anything, but we consider only value, say 16. Now, and the value is given, that is profit. So what we have is, it should not increase and the profit should be maximum. So how many items are there? 4 items, or you can say objects. What is the weight given? For 1 it is 2, for 2 is 5. Approximately you have the values, that is profit, given in dollars. You can give only 20 also. So how to solve this? So I'll take a subset. So what is the idea of it? The capacity should not exceed more than 16. So again this is given. For first item weight 2, what is the value? 20. So it is filled. So for fourth subset, you can see it is $10. Now we'll have a combination. How we'll write a combination with a subset? Say if I say 1, 2. What is 1, 2? 1, 2. So 2 plus 5. What is 2 plus 5? It is 7. What is the value for 2? It is 20. What is the value of 5? It is 30. So 20 plus 30 is how much? 50. Like this, you can't keep on writing the subset. See, for 1, 3 it is 12, and if you add, it is 70. Similarly, we have written a lot of examples here, but where shall we consider? How much shall we consider is, we have to take the maximum profit and it should not exceed 16 capacity of the knapsack. So next, here they had given not feasible. Why not feasible? See, the capacity, it is 17. We don't want 17. It should be below 16 or equal to 16 also. Whereas this, it is below 16. But in this, which is the more profit you have to consider? Which is the more profit? If I say 20, 30, 50, so which I can see is 80. So 80 is having the highest profit with what is the weight? Weight is 15. So this is my optimal solution, best solution among this. Not feasible I won't take because it has exceeded the capacity. So this exhaustive search, where and all it can be used? It can be used for a Euler circuits to find the shortest path, as we found out in the traveling salesman problem. And minimum spanning tree. What is a tree? What is a spanning? Why it is called MST? We say minimum spanning tree has MST. This will be discussed in your next unit. Okay. Next, the assignment problem. You all know that there will be 4 person or 3 person. Each person will be assigned some job. How will we assign the job to particular person? That is about assignment problem. It is also under which search? Exhaustive search. So, now we'll go to a graph related problems. What is the graph? In the graph traversal, we'll have 2 types. According to your textbook, it is DFS, depth first search, and BFS. What is depth first search? We'll visit all the nodes until the last. Say we'll visit the children or leaf. Whereas breadth first search, what we do is we visit the siblings, or we can say we'll visit all the levels. Okay. This is graph traversal. Traversal means visit. What to visit? Visit all the vertices or nodes in a graph. So before going to the graph, BFS and the DFS, we'll have some terms of it. What are the graph? How we'll say graph? A graph will have a set of vertices and edges. Vertices we have already discussed, and edges also has been discussed. So edges may have weights, and here you have another point, directed graph. We already discussed this in undirected graph. What is directed graph? Edges having direction, that is arrow mark. And what are the other problems will come here? Along with the TSP, we have topological sorting. Next, we'll discuss about this DFS and BFS. Then, after graph, we have another terminology, tree. When it is a tree, it is acyclic graph. What is a cycle then? Cycle means, if I say cycle, there is a loop. The best example I always give is A, B, C. What is this? These are the vertices. I'll connect with the edges. See, this is a loop. From A to B, B to C, again A. So it is keep on going. That is cycle. This is a graph, but it is not a tree. Because a tree should be acyclic graph. If I take A, B, C, this is a tree. No cycles are there. So when I say tree, you should write it acyclic graph. So it has n nodes. A, B, C are the nodes. N minus 1 edges. How many nodes are there? 3 nodes. How many edges should be there? 3 minus 1, that is 2 edges. So first edge, second edge. Correct, right? Next. Then what is forest? We all know forest is nothing but collection of trees. We say set of trees. Next, connected graph. So every pair of vertices has a path between them. So from A to B I have a path. From A to C also I have a path. Then every pair of vertices has an edge between them. So every vertex from A to B also I have a edge. A to C also I have a edge. If you have all the edges between all the vertices, then it is called complete graph. Okay. Next, what is adjacency matrix? See, matrix is rows and columns. What we do is, we'll take, say, 2 rows and 2 columns. So, from 1 to 1 and this 2 to 2 will not have any cost. So, what is the cost from 1 to 2? See, if there is a graph, say 1 to 2. I have taken only 2. We don't take only 2. We'll take more than that. And what is 1 to 2? If I have some path, say 5, 1 to 2 also 5, 2 to 1 also 5. That is cost adjacency matrix. See, we have written in rows and columns. We have written the cost. Adjacent is if there is an edge from that particular vertex, adjacent. That will be written. You can't write simply. Only if there is an edge and cost, you have written. So, we'll denote 0/1 for edge or not. If there is an edge, we can denote 1. If there is a no edge, 0. See, we have denoted 0. See, diagonally. Next, undirected graph means what kind of matrix it has. Next, when we go to DFS. So, what is DFS? What is the full form? It is depth first search. How it should do is visit the graph's vertices. First, we have to visit the vertices in a graph, always moving away from the last vertex. That is, we have to start from the depth, that is children or a leaf node. Then suppose if there is no adjacent node, I need to come back to the first one. What I do is, I'll backtrack, say reverse. That is only possible in DFS. Say when I say BFS, no backtracking. Backtrack if no adjacent unvisited vertex is available. So backtrack only when unvisited vertex is available. So DFS uses a stack to push the elements. Elements means here it is the vertex, and even pop the element. So vertex is pushed when it is reached for the first time. First time when you visit, you'll push it to the stack. When the vertex is popped, popped means deleted. When it becomes a dead end, meaning to say when there is no adjacent unvisited vertex. So each time we mark the edges in a tree-like fashion. Now we'll start with the algorithm. How to write an algorithm? When we want to implement DFS, we'll start with the input. What input will give? It's obviously graph. A graph contains what? Vertices and edges. V for vertices, E for edges. So graph G with its vertex marked with the consecutive integers. First we have to check what and all it is marked. Next. So for the first time we keep a counter that is assigned to 0. This is 0. For each vertex V in capital V. So V is a vertex to be visited. First time V will be marked with 0. So that time we will call a function DFS of V. We are passing what? Vertex. Next, all the times you have to recursively visit, which you have not visited the vertex, you have to visit at least once. Then each time the count will be incremented. So this is an example for how to write this in a DFS. So first time we told that it works on a stack. The very first is nodes is pushed here. Where? In the stack. So I'll take A. From A it will go to BF. So BF is visited. So from A it goes to B, then F. Then what happens? Another edge is there, so you can write down E also. So A, B, E. This completes. Next we can write G. G is connected to this B, so G is written. Then C, D, H. So all the nodes are there, A, B, C, D, E, F, G, H. What we have to do is, we have to push the elements into the stack. So what is the order given here? It is, first is A, B, F, E, then G, C, D, H. So all the elements have been visited. This is about DFS. DFS can be implemented with the graphs represent. So if I want to take a adjacency matrix, what is the complexity? It is big O of V square. If I take the list, we consider V and E. That is vertices and edges. Then, so where and all this is used? This can be also used in the scheduling and topological sorting. So what are the applications of it? We already know this application. It is useful where? Checking the connectivity. We return a graph to check what and all that's connected to which vertex. Next, it should be acyclicity. Next is BFS. Breadth first search is different with the DFS. What is the difference here? So this also visit the graph vertices by moving across all the neighbors. Which and all vertices are connected, we keep on marking the vertices. Next, it doesn't implement stack like DFS. BFS will implement queue. So it is level by level. Here we don't go into depth, we don't go into the children, level by level we will write. So same procedure, mark the edges in the tree like fashion. Next, similarly, same procedure in this also. What's the difference here? It starts with the algorithm BFS. We have given an input as G. G is a graph. So G is equal to V comma E. So V is a vertices, E is edges. So what is the output? We'll have all the vertices marked with a consecutive integer. Next, counter is assigned to 0. So for each vertex in V, for the very first time, V is marked with 0. And we'll call BFS function by passing vertex. So next we have to visit all the unvisited vertex. Each time the count will be incremented. Now it is in the queue. We have to check whether queue is not empty. With the very first time queue is empty. So until queue is not empty, for each vertex in W, all the adjacent vertex we have to check. Then W will be marked with 0 and each time inside the while loop we'll increment the count. Then remove the front vertex from the queue. What is visited, we'll just remove it. So this also BFS traversal queue will keep on the levels. Okay. The very first example is same. I'll gonna write A is connected to B. A is also connected to F and E. Okay. I'll write this as level 1. This as level 2. And next, from B it is connected to G. Okay. From G is also connected to H and C. From C it is also connected to D. So these are the levels. So anything it is missing, you can connect the edges. Say this is level 3. Similarly, it goes on. So first we have to write all the level 1. See, level 1 is A. So how to write BFS traversal queue? A. Next, second level we have to write this B, E, F. Next, third level we have to write this G. Next, HC also you can write or CH. Last level is D. So how many levels was there? 4, 5. These are the levels. Okay. This is breadth first search. So this is similar to your DFS, where if I say DFS, it is depth. From the depth you have to start. From this, here you can start. So this is the example of breadth first search. So what are the application where it is useful? First we look into the adjacency matrix. If I say matrix, I will consider vertices. For list, both the vertices and edges, and is denoted by big O. So the application for BFS is also similar for which one? DFS. So based on this example, we can say that our brute force is used in our sorting, exhaustive search, even TSP, knapsack, even more pattern matching. If I give a string, I should match with that string. Then if I take a graph, it is DFS and BFS. But if I say brute force, it is based on the problem statement and definition. So it is straightforward. Depending on this problem statement, we'll define the solution of it. Better algorithm frequently known. You know the algorithm, the problem you can use with the brute force. So what are the examples? These are the examples in brute force method. Then what is the strength of the brute force? See, strength is wide applicability. So wide application, it is used in this method. And it is very simple to understand also, brute force. Reasonable algorithm for some important problems. For some important, not all the problems, some important problems, it will yield what? Reasonable. And the algorithm may be good enough for smaller problem. This is the important topic. So if I say brute force, only smaller problem. For larger problem, this won't suit. So improvement may be too hard. This can be used in brute force. Then what are the weakness? So rarely yields efficient algorithm. Sometime you may not get efficient algorithm using brute force. So this is also one more disadvantage. It is slow. We need fast algorithm. It is not as constructive as some other design techniques. If you go to other algorithm in the next unit, you have divide and conquer. If you compare that, it is not that constructive. So this completes your brute force technique. In the next section, we'll be discussing about divide and conquer. Thank you.